Okay, so I guess we can continue. I will start with the question that was raised just before the break about how you know whether or not this passed. Well, I looked it up, and it's actually, you don't really need to put up any if statement at all. Basically, it's like many of these other OpenGL functions that when this pass, it's the input to this one that really tells you what to do if it passes, and then it's taken care of. So you basically have a option in this function that you set what to do whenever this function passes. So no if statement. You just put this one down, and then whatever you have placed into I think the second slot of this function will decide what to do whenever the test passes or fails, for that matter. Okay, so that makes it a bit simpler and you avoid some code lines. Right, so if there's no questions about this stencil buffer business, I can move on to the main topic page, basically, which is shadow maps, which is what we will deal with most likely here if you want to implement this thing. So it's capable of dealing with quite complex geometries, no, I don't necessarily think you can do that with the stencil test. But there's probably a test that may do it, but that's not related to depth or test buffer. I think that terminating the program, you probably has to deal with window functions or something in GLFW, most likely. So these tests are basically connected to the buffer they're named for, and what operations you do on those ones. Okay, this shadow mapping is also quite easy to compute, so that's usually where you start off. Now, if you have only one light source, you have to render twice, and if you have several light sources, you have to render this the number of light sources you have times, and then one more time as the usual rendering. But that is actually in many other algorithms you have to render even more. And the point is that first you render the scene from the light's perspective. So take this scene here, for example. We now have this from our eye perspective, but the light perspective would be up here somewhere, right? So you render it from the light's perspective to create this shadow map. And then you only render it to the depth buffer. So you don't render this to put it on the screen, but just to get some depth values in the depth buffer. And then you will take this depth buffer values, which is basically a value giving the depth for every pixel in the image, and you will store this as a shadow map, and that you will store as a texture actually. And then you will get this map shown here, which basically shows you the depth of the image given the different levels of gray here. So it's a grayscale image that works as a texture. And then you render the scene again, as usual, and use this shadow map. And then you transform every object to the light space, as seen from the light, and then you do this comparison of C values. And if you have a value in the C buffer for that given fragment that is smaller than the object's C value, it means that your object is in shadow. So for example, if you have a fragment lying over here, seen from your point of view, seen from the light's point of view, there is something in this depth buffer, or in this shadow map that you made, that is closer to the light source, meaning that the point you have over here will be occluded. And whenever this test here tells you that you're in shadow, you can either eliminate the lighting in this point or attenuate it, put it to a low value so you get the impression that this area is in shadow. Okay, so to a little bit more detail, I will take the simplest example I can, which is basically a shadow mapping with directional light. And to just repeat what directional light is basically light that is the same, that comes from one direction and is the same. It doesn't really have any spotlight effect, so it's basically the same all over and coming from one direction. For example, under sunlight, for example, this is approximately a directional light source. And then basically, as I said, you render twice. So you transform yourself to the light source, and then you compute the distances from the light source onto the nearest object for each and every pixel in the image, basically. So you estimate all these depth values. And then of course when you render again, if you have some point ending up in here, then you know that that one will be in shadow. But instead of talking about this into thin air, I'll try to go through this code line by code line, how you can implement this thing. So any questions before I do that? Okay. So here's how you go about. So you have two renderings. I'll now talk about the first pass first. And in the first pass you have to do two things. You have to create a frame buffer and a depth texture. And then in the shaders you have to make sure that you transform all the vertices to the light's perspective. So I'll just show first how you create a buffer, and then on the next slide I'll show how to transform to the light perspective, and also how you create the shaders. So first and foremost you need to create a frame buffer. And creating a frame buffer is just like you create any other buffer in OpenGL. So you give it a name, and you just use this GL gen frame buffer. You generate one buffer in this case because that's what we need. You add a name to it, and then you bind it. So now this is bound and you can work on it basically, just like you have to bind any other buffer that you want to use. And it's a target is of course a frame buffer with that particular name. And then you have to create a texture where you want this frame buffer to be stored so that you can use it later. And that is just creating a texture in the exact same way as you did before, by giving it a name, by generating it, by binding it, and then store whatever you want in it, and then set these filtering and wrapping parameters here. The only difference here is that the layout in this GL text storage, or in this GL text image 2D, depending on what you use, is different. So you have to choose GL depth component, and this number here tells you the number of bits you have per pixel basically to store depth. So here it's 16. You could have 32, but usually 16 I think is way is enough for these shadow maps. And then the key comes here. You call this function GL frame buffer texture, and of course the target is the frame buffer again. And then you say that I'm going to have a depth buffer attachment. So the second thing you put in here is the type of attachment. If this would be stencil, of course it would be something else here, but this is depth buffer. So when you call this, I have frame buffer with a depth buffer attachment, and this content I will put into my texture here. So whenever you now call draw, then that command will basically take whatever you have in this frame buffer, which is basically connected to the depth buffer, and it will be loaded into this texture you created here. So now you have this depth map at your disposal after the first rendering. And of course when you render you put in GL none because you don't want to render this to the screen. So you just want to render it to the depth buffer and then keep whatever is there. So that's how you go about to do this. And of course, when you call draw, you need some shaders running in the background, right? And they're pretty simple and straightforward. First and foremost, you have to make sure you transform to the light's perspective. And here we are actually going to deal, one of the few times we deal with it in this course, about orthographic projections. I don't know if you remember what that was. So since we have directional light, the type of projection we have to the light source will be of this kind. If you remember back to the talk we had on transformations. The other possibility is, of course, perspective projection. But for directional light, you basically have this sort. So that's the main difference. You also have the possibility to set a perspective projection in this algorithm. But then you no longer have a directional light. Anybody has an idea what sort of light you would have if you assumed a perspective projection? Well, that's a very common thing to think, that it will be a point light. But remember, a point light goes in all directions, right? So it is a point light, but with a restriction, because it will be within a given sort of frustum volume, right? So it will be what you call a spotlight, where you have a point light that is limited to cast light in certain directions. So to go from directional light to spotlight, you can actually exchange these transformations here using perspective matrix here instead of the orthographic one. Okay, so I'll go through this line by line. So first and foremost, you have a light position, and then you have this depth projection matrix, which is in this case the orthographic one. And it's simpler to set, actually, or at least not more difficult than it is to set the perspective one. So you need to define what is left and right of your scene, what is top and bottom, and what is near and far plane. So it's many of the same things, but it's a bit more clear and explicit what you will set here. And then the key here is to see this from the light perspective. So when you make a look-at matrix, you of course still look at the origin, blah blah blah, and up vector is the vector pointing up is the y-axis. But instead of putting your eye position in here, you put the light position in the look-at matrix. And then of course you may have this model matrix for this, which is just TRS, as we've seen before. And then your depth transformation matrix, which is basically turning the scene from the point of view of the light, is basically the projection of projection matrix, view matrix, and depth matrix as before. Or I mean, sorry, model matrix as before. And then you do like you do with any other transformation that you want to connect to your vertex shader. You make a uniform, so a GL uniform matrix, and it's a 4x4 this time because it's a 4x4 homogeneous one. And you basically do like before, same procedure. And then of course you make this uniform here in the vertex shader, where you now have this transform available, so that you can take all your input vertex positions given up here, and then just transform them to the light's perspective. And then you have the fragment shader. Now the cache here is actually, this is done by default, I think, in this mode. At least that's what they say. So you may not have to write it explicitly, but just to show what it does, it's like this. You have an output from the fragment shader, and that is basically just this C value of your fragment coordinates that are stored in here. And then of course, when you then draw here, the value in that depth buffer will be loaded into your texture, which now contains all the depths in your scene. Any questions to this? Understandable? Anyways, we will we will have a lab on this, which we'll make available, which is voluntarily for you to deal with, and then you can play a little bit around with this and get a better grasp of it. But it's quite similar to what you did before. You just have to always think in this first pass about the depth buffer and also the light perspective. Ah, yes, yeah, sorry, this is just a mistake. It should be the same, of course. I wasn't too thorough when I went through this, I see. Yeah, so it's 450, of course, in both of them, in this case, or whatever version that your system is supporting. Right. But anyways, this fragment shader I think is optional in this case, because it's done by default when you call draw under these circumstances that you set. But you need to make sure you transform your vertices to the light perspective. Alright, so what you typically end up with, if this is your actual scene, now it's shown with shadow, and the shadow map will basically be this grayscale image, where black is actually closest to the light source, meaning that it's close to 0 value, so it's dark gray, and white is the most remote part of the scene. And of course, the lighter, the most, if the light is up to the corner here, then of course these parts will be furthest away, so they have a lighter gray tone. No. I mean, no problem with the 410 core. That should be no problem. You don't use anything here, I think, that requires any newer version. So I think this should go fine. I think that I think I fixed this one actually. I think that originally this code, which is this example, which is given in one of these OpenGL tutorials, they had 330. So I think that should be fine. And by the way, if you would like to look at this code in more detail, you find this tutorial. It's quite nice if you want to go through this step by step. They also add some other things that I won't talk about today in order to make your shadows look nicer and those sort of things. Okay, so this is a typical shadow map texture, and now we can use this to tell you whether a fragment is closer to the light source than any of the contents in this buffer, right? So now you've done the first pass, you have this this shadow map available, and now you go to the second path, which is applying this one in rendering the scene. Yeah, that's the first thing first. You need to resolve the fact that there's a difference between texture coordinates, which your depth map is in, and of course the vertex position, which goes from -1 to 1. So this has a center 0.5, 0.5, well this is a center at 0, right? And that you just do by some bias matrix. I've chosen not to show it here now. It's a lower triangle matrix with just 0.5s in it. But you multiply your transform with that one to make sure that you are in the same sort of coordinate system. So this is just a trick you do to make things correspond here. Now I won't show the full shaders in this particular case, because I just need to show the essentials. So in the second pass, when you do the rendering, you of course pass things to the shader as you used to, but the difference is that now you have two outputs that you will forward to one you will forward to the fragment shader. The second one is basically just the standard GL positions. So first you have the positions as seen from the camera of the eyes, which is passed in a normal way. So you have your your movement, your view and projection transform times whatever positions you have in your model space, as usual. And then you have a set of shadow coordinates, which is basically the same vertex coordinates but transformed to the perspective of the light. So you use this transform to do that, but with this bias taken into account. All right. And then in the fragment shader, there's the main key of what you do. So you use this texture, which is basically the command saying that in my fragment shader you interpolate in this way, you use this shadow map, and you have these texture coordinates, right? But now you don't use it to put it on the screen. Now you use its C value to do some testing. So this command basically gives you the depth of your shadow map, basically, when you have these sort of texture coordinates. And you do similar things as you did when you have normal textures, only that, so you have bound one texture here, right? But this time, instead of using sampler 2D texture, you use sampler 2D shadow. It's basically a sampler that is more tailored towards shadows, basically. And then you basically have your shadow map, which you constructed in the first pass of the algorithm, or the first rendering. And then you make a couple of floats. So one float is the so-called visibility term. This is the one you will multiply with your lighting to make it appear in full light in certain places and darker in other places. And you will also need this bias in order to avoid some nasty effects in the when you cast the shadows onto your scene. Now, why this is done is explained in this tutorial. I won't go through it again, but it's removing something called a shadow acne, which is a sort of like weird pattern that shows up in your lit areas. But you can very simply fix that by adding this bias in this if sentence here. But back to the point. You have your shadow map. You have this this depth of your given shadow map, and then you basically make this if. For each fragment, you make this if statement. So you take this this depth in your shadow map and see if that distance is smaller than your current shadow coordinates C value, minus this bias. And of course, if this one is smaller, it means that whatever fragment coordinates you have here will be in shadow. And then for those fragments, you set the visibility term to some number close to 0. And when you then compute your out color, you take your ambient color, which is untouched by the shadow, and then you multiply this visibility term with the specular, the diffuse, and the specular components of your light. And then of course this is done fragment by fragment, and every time the depth test fails, you set this to a small value, and whenever it passes, you just set it to 1, so you have full light. So now you basically have your basic shadow casting. But to get a nice result like this, and avoid aliasing effects and all those things, you have to do additional operations. So this goes to say how difficult this subject is, because it's not enough to just do this, you have to do other things. So one is to deal with this shadow acne thing, which is done by adding this bias. This bias can be a small number, or it can also be, you can have some cosine function or something in there. But this is explained in this tutorial. I simply don't have time to push all this through in one lecture. And to avoid aliasing effects that may also show up in this case, you can use something called Poisson sampling to resample your image to be sure that you avoid aliasing. But again, all of this is described in this tutorial, and one of the labs we will put out next week will also deal with this one. So, but this is basically, I think, already implemented for you, so you can just look at it and see what it does. So that was the basics of shadow mapping. Do you have any questions about this before I move on to shadow volumes? Okay. Right, so now we talked about shadow map, and as I said, depending on what projection matrix you use, you could deal with mainly 2 light sources. It's spotlight, which we didn't show now, and directional light, which I just shown. But if you want to model point light, for example, or area light, this doesn't really work very nicely. You can do it, but it doesn't look realistic. So to deal with these cases, you have to go to something called shadow volumes. So the good thing about these volumes is that they can cope with a broader set of light sources, but the trouble is that they're much harder to compute. But I'll just go through the principles. So I think shadow volumes was first time used in a game called Doom 3. That's where they were able to implement this for the first time. I think the principle is pretty old. I think it's back to even the 70s maybe, or 80s. These techniques has been existing for a long time, but you didn't really have the computational resources to implement them. But in this game they were capable of doing that, and that was because I found a neat way of doing the computation. So the basic step is that you will create a volume that represents your shadow, and everything that's within that volume will be in shadow. And the steps of doing this is that you have to find all so-called silhouette edges. And these are edges which is basically separating front-facing faces from the back-facing faces, to say it like that. It's a bit messy wording, but I can show it like here. So if you have some occluding object, you have your front faces here, and you have your back faces on this object, and the silhouette edges are basically those edges that goes from the lit sides over to the dark sides. So this is an edge, for example, and here the edge is basically mainly just a point. So you have to figure out what those edges are, and then you extend these silhouette edges away from the light source, so you get this this volume here. Ideally you extend it to infinity, but that's a theoretical thing. In reality you cut them off at some value, and that depends of course on the depth of your scene. So the point is here that you have some point light, it will cast a shadow like this cone. It always casts shadows like cones. And for every occluding object you will have another cone. And whenever an object falls in this cone, it will not be lit. So the principle is quite simple. If you have some larger object, a part of that object inside the cone will of course be shaded, and the ones outside will just have normal illumination. So, but that's of course easy to say. How do you compute this thing? It's a different story. So in a more complex situation, of course, you will have several occluding objects. Here I just draw them as bars because it's just to illustrate the principle. But for each occluder in this space, you will get this shadow cone. So here we have one shadow cone, here we have another shadow cone, and here we have a third shadow cone. And this, of course, makes things much more complicated. But it's not that hard, actually, because each of these cones will have something we call a front face, which is the part that is facing the viewer, and it will have a back face, which is on the other side of the object. And what you can do to figure out whether an object is inside this shadowed area or outside here is to count the number of front and back faces. So what you have to do, you have to figure out what these edges are, and you have to render these shadow volumes, and then these shadow volumes will just be polygons like any other thing you render in OpenGL. And for example, if an object is outside here, then if you count a positive value every time you cross a front face, and you decrement every time you meet a back face, then of course if you're within a shadow here somewhere, the sum of all these numbers will add up to something that is different from 0. And whereas you're outside this shaded area, these numbers you add and the numbers you subtract when you pass the back faces will add up to 0. So that's how you will test whether you are in a shadow or not. So is this okay, understandable? Any questions to this?
The numbers, what do we use them for? Like the +3, +2, what are their, well, like how do we use them in our computations?
That's a good question. This is where the stencil buffer comes into play again. So now we use the stencil buffer, but we use it differently. We use the stencil buffer to for each fragment to increment. So when you render each fragment, and for each fragment you will figure out whether you're in its shadow or not, and that you will see from the value you have in the stencil buffer. And that's actually how you do the counting. So just to take it again, if I look in this direction, for example, and I have some object in here, when I pass the first edge I set +1. I pass the second edge I add 1 again, so I get +2. At the third one I get +3, and then I pass a back face, and then I decrement, and I get, of course, +2 again, and so on and so forth. So my stencil buffer value will end up being +2 for that particular pixel. Yeah.
Does that mean that the +3 means that there will be a darker shadow in that area?
That's a bit of a fancy thing. You have the possibility to do that here, actually. So you could just put it white and black, or I think you could use these numbers also a bit cleverly to say that I put this darker, and then the rendering will look more realistic. So that's absolutely an option. So here's an example on how you do this. So basically, if an object is outside the cone, all the front faces and back faces adds up to 0. So it means that this one should be fully lit. And then, of course, everything inside here, just as was said, can have other values. Yeah.
How do we know we have passed a shadow column? It's like there's like a coordinate to it, or how do we know we have passed a column?
You have to render each volume, basically. So all these shadows volume has to be rendered, and that's why this is a bit computationally expensive. And of course, then you know every time you have a polygon, you basically have to add a number, right? When you go for your scene in one direction, you will basically have you know, X number of polygons lying there ready to be drawn. Did that answer your question?
Yeah.
So what you see here is called a C pass, and it's called C because this is, of course, again related to the depth buffer. The C pass is not so good because if your camera is within a shadow, it doesn't work. So what you usually implement is something called a depth fail, which is a C fail method. So I'll talk about that. It's a bit different from this, but the main difference is that in the C pass, if you have an object over here, you will count and count up and count down and end up at 0. Whereas if you have a C fail, this object will just not be counted, so it will stay 0. It's the objects in front that will be counted. So I'll try to explain. So basically, here is how the depth fail method works. You have to construct a stencil mask from this scene depth information, and you make holes wherever you figure out that something is not in shadow, and then you render the scene again with a full lighting. But of course you also have to render these different volumes, so there's a lot of rendering going on, but you at least need to have these 2 steps. But in finding the stencil mask, of course, you need to render several times. And then you update the stencil buffers as follow. And here we call it depth fail. So first and foremost, you disable writes to your depth and color buffers, so that you don't overwrite them. And then you use so-called front face culling. This is a condition you set in this test method. You can set GL front or GL back, or you can set GL front cull or GL back cull. I don't remember exactly the name, but you have those commands in OpenGL. So you use front face culling, meaning that you are looking at only front faces. So this face, and this face here. In this case with 3 shadow volumes. And then every time you pass one of those, sorry, that was completely wrong. Whenever you have your object lying somewhere, so let's say your object is lying within here, it means that that object is deeper than those two. Right? And therefore, the depth test for that object fails. So let me see if I get this right. Ah, no, sorry. Then of course the depth test passes. So if an object is in here, then the depth test passes for those two because they are closer to the eye than your object. And then all the other ones behind here will fail, and therefore you will get a number different than 0. Same thing, then you use backface culling and you decrement your stencil buffer every time the depth test fails. So then we have 3 possibilities. You can have the object in front. This means that all the depth test fails, both for front-facing and back-facing faces. So if you have an object in front, you count +1, +2, +3, then -1, -1, -1, and you end up at 0. If you have an object deep in the scene, it means that the depth test always passes. And when the depth test passes, you don't do anything, basically. So you end up having a 0 in your initial stencil buffer. And if your object is, for example, at this place, then the depth test will pass on all of these edges here, but it will fail on those two, so you will decrement 2 times and end up with a number that is -2, which tells you that that you're within a shadow. Basically. Yeah, and here we may see that using these numbers directly for casting shadow is not that straightforward, because exactly what number you have will depend a bit. I think I think it may still be used. Yeah, it's just that you have to be a bit careful on how you use them when you put in lighter and darker regions. So it's a bit more complicated, but it's quite straightforward. Basically incrementing the stencil buffer based on this back face and front face culling, and then using the depth test, feeding that back to your stencil buffer and do something with that depending on whether that test fails or passes. So that's it for the shadow volume technique. Do you have any questions for this one? Okay, so you will probably not deal with this in this course, but a step ahead, this will probably be the direction to go, because now you can deal with more interesting light sources. Of course, if you were able to implement that, that would be very impressive. But it goes to say that there are some smart ways of using these buffers in order to figure out how to shadow objects. Right, so there's little time left. So I'll try to just skip through this fast and not go into many details. Of course, I didn't talk about how you decide these silhouette edges. Those edges you use on your objects to cast the shadows that follows. Luckily, it happens that in image coding you have a lot of techniques on detecting edges in images. So what you basically do is to use these edge detecting techniques on your C buffer values, and then you'll figure out what these C edges are. But you don't need to worry about it now unless you continue with image coding, because they're basically there at your disposal to do this thing. Then of course you have the problem with soft shadows. We saw one way that you may look at this by using the stencil buffer, and you could also use the stencil buffer to make a sort of wedged area outside every hard shadow, and then just fill it with different values so that you get some gradual takeoff from gray to white. Or if you're looking into this shadow mapping, which we just talked about, I think a good option there would be filtering. Because if you filter your edges, they will be a bit smoother. They will not go from entirely black to entirely white, but you will have some gray shades in between. And depending on how smoothly you filter something, it will look more realistic. Of course, it's not physically accurate, but it looks a bit more. It looks a bit better. So that's how you may deal with soft shadows, at least at this more rudimentary level. Of course, in a real scene you will have multiple lights, and then you will just have to do the same procedure per light source. So for example, as shown in this picture here, you have 4 light sources casting 4 different shadows, Now you have to make 4 shadow maps, which means that you have to render this scene 4 times to obtain those 4 textures, and then you will have to add them all together in the 5th and final pass. So you need to render this scene 5 times in order to get this. So it sort of goes without saying that that rendering shadows is quite expensive. Right. Of course, in a real scenario, you would like something to look like this. And now it really starts to get complicated because you have to take into account that you have mist, fog, water spray, scattering from droplets, all that stuff. If you're capable of doing it, you can get some really, really nice renderings, but doing this in real time is not an easy task. So you may use extensions of some of the methods we talked about today, for example, shadow volumes, and some stencil testing to do these things in reality. I won't talk about them today because it's far beyond the curriculum of this course, but there's possibilities there. And of course it goes without saying that it will be very costly hardware-wise in the number of computations. If you're interested in this, there's an example on fog modeling in the Super Bible on page 605 to 609. But it has to use these tessellation shaders, which we haven't talked about at all, so I won't really go into it. But there's some methods that can be done quite simply, and from this you can get some quite impressive renderings. And of course, the last thing, there are other challenges, like for example refractions and transmission. So how would one go about to make a shadow like this? That is not simple either. So this last example is just to conclude, or this whole talk is basically showing you that dealing with shadows is difficult, both conceptually but also computationally. So there's a lot of research going on in graphics, I think, has to do about making realistic shadows. So there's a lot of tasks there that still needs to be solved and can produce many, I think, both bachelor and master theses to come, and also a PhD level, I would suppose. So that's my end. I listed the resources I used here. Super Bible, there are several pages in there. They talk about stencil depth testing, they talk about frame buffers, and they talk about shadow mapping. And you also have this tutorial, which I took the code from. You also have several resources talking about shadow volumes in more and more depth. Here is one that is particularly, this one is particularly towards stencil buffers and those sort of things. And you have this video in the bottom here, which talks about this simplest method I talked about in the beginning. And it also talks about shadow volumes to more depth if you would like to see that one. So I think that's it for now. Do you have any questions? Comments?
Yeah, with shadow mapping and the shadow, kind of the second thing, when you have to choose which one to go for, what is the thought process which you take into account, and can actually have both, or do you have to choose either go with shadow map or shadow volume?
I think that if you have a rather simple lighting situation, like you consider directional light or spotlight, then you definitely go for shadow map because it's easier. If you want some more advanced lighting in your scene, then you probably go for shadow volumes, because then that will take care of all the lights in your scene. So I think that's it. If you use shadow volumes, you don't use the shadowing map. If you have the possibility to use the shadow map and its physical accuracy is not that important, you use shadow map all the way. But then of course you can't cope with point lights and area lights. And I think yeah, if you light the scene at this stage in graphics programming, you will mainly do that with some directional light of some sort. So you can basically get away with the shadow map. Any other questions? All right. We will put out the lab on this next week, so you can play a bit around with this if you're interested. It's sort of like the next step of graphics programming. So this is why we sort of add this as a obligatory part of the curriculum. So next week, I think also Carl will have a presentation on CMake. So he will get back to how he does that later when he has had time to clear his schedule. So we will inform you during the weekend through Wiki what we will do. But I think we will also continue to send these Blackboard messages because it's really a way to get this out to everyone once we decide on what to do. It's not so easy to decide that now as it was when things were functioning as normal. So yeah, that's just how it has to be.
About the presentations for the assignment 2, will we do it as groups will come on Blackboard and present it to you or to us, or we choose how we want to present it?
I think we definitely will present it in this engine. So whether we will end up doing it group-wise, just with me and Carl and Leon present, or we will do it for everyone in this common room like we do now, it will be one of those options, but I think we will decide when we get closer and we have gotten a bit more used to this thing, so we know what's the best to do. Yeah. And I think that also the oral exam will probably be done here, but that will be on a person-by-person basis with me, and probably Carl and Leon may also be on that session to ask questions. So yeah, but we'll get back to those things later. I'm sure that this course will be able to finish as usual. So yeah. That's good thing about having home exam also, that we don't need to deal with that situation now. It's basically the same. So any other questions for now? Okay, then I think we're at ways end, and I will inform you later what happens in next week when I know more about that. So then you have to yeah. So goodbye, and I'll talk to you then, and yeah, have a nice weekend.